In the last segment, we began looking at chemical bonds. We examined ionic bonds, which are an attraction of oppositely charged particles. We first formed some charged particles called ions. Ions form because some atoms will give up or accept an electron in an effort to achieve a filled valence shell. We will now look at a covalent bond. A covalent bond occurs when atoms share outer electrons. They are still going to share these outer electrons in an effort to fill their valence shell. Let's look at chlorine. Chlorine is atomic number 17, so 17 protons, 17 electrons. If we do our electron configuration once again for chlorine, we have 2 electrons in the first shell. We have 8 in the second. That's 10. That leaves 7 electrons in the outer shell. Chlorine would like to have one more to fill its outer shell. So what if 2 chlorine atoms get together and they agree to each share one of their outer electrons? This would be a covalent bond, where these outer electrons, this single pair of outer electrons, is actually shared. So now if we count the valence electrons, we have 1, 2, 3, 4, 5, 6, 7, 8. So this chlorine has a filled shell. If we count the valence electrons in the other one, 1, 2, 3, 4, 5, 6, 7, 8. Everybody's happy. This is called a single covalent bond. In a single covalent bond, each atom contributes 1 electron or shares 1 electron, and so 1 pair is shared. Look at another example. This is hydrogen. Hydrogen is atomic number 1. So it has 1 proton, it has 1 electron. That 1 electron begins in that first electron shell. That shell will hold up to 2. So once again, we can have 2 hydrogen atoms. Each of them agrees to share an electron. And so we have our bonding pair of electrons. This again is a single covalent bond. We can write that as the structural formula, and so whenever we do that, we use a single dash, and that represents a single covalent bond. So this dash represents 1 pair of shared electrons. Or we can write the molecular formula, where we use the H with the subscript 2, and that indicates there are 2 atoms of hydrogen in this molecule. Here's one that's a little more complex. This molecule is methane Ch4. And so looking over here at the structural formula, this indicates there is 1 carbon and 4 hydrogen atoms in this molecule. Okay, let's see why this molecule is going to form. Begin with carbon, atomic number 6. So carbon has 2 electrons in its first shell. It's going to begin with 4 electrons in its outer shell, and so it would like to have 4 additional valence electrons. Each of these hydrogens began with 1 valence electron. So if 4 separate hydrogen atoms agree to share their outer electron with a single carbon, and carbon shares 1 of its outer electrons with each of the 4 hydrogens, we can form 4 separate single covalent bonds, right? Or a methane molecule. Once again, we could count valence electrons for each of these hydrogens. They have 2. If we count the valence electrons here for the carbon, carbon has 8 in its second shell, which is its outer shell. And so this forms a stable molecule. This is an oxygen molecule, O2, which is oxygen gas. So we begin with 2 atoms of oxygen. Oxygen is atomic number 8, so it will have 8 electrons. That would be 2 in the first shell. That leaves 6 in the second shell. Each of these oxygen atoms would like to have 2 additional electrons to fill the second shell. So now if 2 oxygen atoms each agree to share 2 of their valence electrons, we can form a double covalent bond. In a double covalent bond, each atom contributes or shares 2 electrons, so there are 2 pairs that are shared. Okay? But what is accomplished now, again, is each atom has 8 electrons in its outer shell, and that's going to create the stable configuration. Whenever we write the structural formula, we use 2 dashes, and 2 dashes represents a double covalent bond or 2 pairs of shared electrons. Now this is very, very important. All covalent bonds are not created equal. In a covalent bond, yes, the electrons are shared, but there are differences in covalent bonds. We have some that are called non-polar covalent bonds, and in a non-polar covalent bond, the electrons are shared equally. And so an example that we just looked at was our methane molecule, CH4. In methane, each of these pairs, we drew these a moment ago, there are 4 pairs of shared electrons, and these are shared equally. And so these electrons spend just as much time orbiting the hydrogen nucleus as they do orbiting the carbon nucleus. And this is true for each of these bonding pairs. In a polar covalent bond, the electrons are not shared equally. And this is very, very important, because if these electrons are not shared equally, that creates a partial charge. Remember, these electrons have a negative charge. Electrons are negatively charged. This represents a water molecule, H2O. So a single oxygen, 2 hydrogens. We have 2 covalent bonds. Here's a covalent bond. Here is another covalent bond. In each case, however, these bonding electrons spend much more time around oxygen and very little time down here around hydrogen. Oxygen is stingy. It tries to steal these electrons away. This is the kid that doesn't like to share his toys. So these electrons in both of these bonds spend more time around oxygen, very little time around hydrogen. These electrons have a negative charge, and so that creates a partial negative charge around the oxygen, and it's going to create a partial positive charge around the hydrogen atoms of the molecule. So polar covalent bonds create polarized molecules. A polarized molecule means there is some charge separation. You have one positive end, you have one negative end, just like the poles of a battery. This is just very critical. Please understand this is very important, because we're looking at water here as an example of a polarized molecule. It's polarized because of these polar covalent bonds. And we are about over 90% water. And so if we want to understand how different molecules are going to react in living cells, we have to know how they're going to react in water. So very important. As we look at some biological molecules, we need to keep in mind that it is normally oxygen and nitrogen that create polar covalent bonds. Oxygen and nitrogen are we say they are electronegative, and atoms that are highly electronegative try to steal electrons. They don't play well with the other children. They try to steal those electrons away. That creates polar covalent bonds, these charge differences, and polarized molecules. Again, very, very important whenever we start looking at these molecules and trying to understand how are they going to behave in a living cell.